Recording in progress.
So, any questions? Okay, so it's a hot day. Yeah. So I almost canceled the lecture, to be honest. I was so sweaty. So we started to talk about F regularity. Okay. So essentially, so far we spent the entire semester saying what it is, and for the rest of the course, at least from the rest of my lectures, I just want to prove a few basic properties, but there are a billion of them. Okay. So the point is, the take home is that F regularity is the gold standard for what it means to be a wonderful singularity. Okay, so they are closely related to F rational singularities. This is the other gold standard. So the point is that these are way better, like these are stronger. Okay? But somehow in certain contexts that we won't discuss too much, these are better behaved. For example, you may have heard of the deformation problem, so these ones are better for that. So you know, this is a bigger class. Therefore, it's of course natural to expect that they perform better, right? Like if you start with something irregular and you do some deformation, you may end up with something irrational. But if you start with irrational, you get a rational thing. So these are like the two important classes of F singularities. And so the philosophy here about them, which
sorry, when you say deformation, what do you mean explicitly?
So there are many types of them. But a particular example is when perhaps you have a family, but I can give you a specific example. You can model by a regular element, and if you know that this has a type of F singularity, you may want to conclude that the ring itself is like that. So the picture is in general that what you want to have is like some family of singularities, and if you look at like a fiber, you want with certain property, you want to say that it's going to deform around that thing, the type of singularities. So yeah, but okay, so what is the philosophy with them? I guess I should have said this a long time ago, but the point is that these are wonderful things. So the thing is that you cannot avoid singularities when you work in algebraic geometry or commutative algebra. It's unavoidable. They just show up. You like it or not. And you would like to still do math, you know, even if you have singularities. And you know, the classical perspective, you know, based on topology, manifolds, is that you never assume singularities. And so out of that, you build theories. Okay? So the point with them is that, okay, if they show up, they are often the basic thing you can have so that the usual geometry holds. Okay? So the point with them, in a nutshell, is to try to prove that they are great. So you want to prove that they have all sort of wonderful properties, and that's what people do. Okay? So we're going to prove basic stuff, but if you want, you can, you know, go ahead and prove all sort of things. So something that was an exercise, well, let me start with the following. We're going to start with the model. Okay? So this is the most basic setup here. But again, to do this, so there was an exercise before. So the point is that if R is a regular, so remember that the regularity notion assumes F by N. So that's implicit. And so here we saw that actually the minimal primes of R cannot, so are pairwise of prime, which geometrically means that the irreducible components of the ring don't intersect. Okay? So by the Chinese-Riemann theorem, that gives you the following decomposition. So RE is an integral domain. And so this is not unbelievable. So look at it, right? So if we have that R is just a pure, we know that it is reduced, right? And reduced just means that this happens generically. But the total rate of fractions of R splits as a product of fields, right? If you assume more regularity, then the same thing happens integrally. Okay? So in principle, you prove this already somewhere in the exercises. It's not an easy exercise actually. I maybe you should have put it as a start, but it's true. And so the point is now what are the properties of these irreducible components? So this is often why you see people that study the regular rings only in the domain case, because they decompose as a product. So my next goal is just to prove that these are normal. These are normal integral domains. You have to study what normality means, but if you want by definition, this means that, okay, if I look at Ri, it's going to be inside its field of fractions. This is field. And I can take the integral closure of that thing inside here, right? This is the ring. Well, it is a ring. It's not trivial that it's a ring, but it's a ring of elements of K that satisfy a monic equation with coefficients in R, right? So these are the elements. Okay. Let me just say monic integral over R. Is that clear? Yes. Something we have seen before. And remember that normal means equality here, right? So this is the integral closure of R inside the field of fractions. And normal means, at least for an integral domain, that it is integrally closed. In other words, that this happens to be inequality. Okay. So to understand normality better, we need to talk about the conductor ideal. Maybe this is something you saw at some point in your computer algebra class, but maybe not. So here I'm just going to define it for domains, but this can be defined for reduced rings and probably more general setups. So in this specific setup, actually I'm just going to look at an integral domain and forget about that I have many of them. So let me look at that. So this is an integral domain. Probably I want to say that it is Noetherian too, which is the case, and so fine, I would say. But this is not part of the definition. So let's suppose that you have an integral domain, and so the conductor ideal. So it's a math frac C of R. Okay. Math frac. Yeah. C of R is by definition the annihilator over R of the R module obtained by taking the quotient of R with R. Okay? So these are, in other words, all the R's in R such that when you multiply R bar by that R, you land inside R. Okay? Or another way to think about it, which is the same thing. Well, I can just write it down here, is to say that R bar is inside the R module inside K generated by 1 over R, right? This is an element of K, and inside K, it generates an R module. So I'm just going to tell you that, okay? So, as an exercise, I'm going to let you prove the following basic properties. You can prove the following. Show that. So this guy is important because this. So it doesn't have to be radical actually. Well, it would be in a second. But actually, something that I'm going to let you prove is that well, this doesn't have to be radical, but for example, it's radical if R is impure. So famous property, but I can tell you exactly what are the prime ideals that contains this guy. This guy cuts out the non-normal locus. These are all the BC here, such that RP is not normal. Okay. So that's the thing about it. In fact, you can prove something a little stronger here. You can prove that this guy is R, i.e., you see, 1 belongs to the conductor, right? If and only if R is known. Okay. There are many characterizations. This is actually the largest ideal of R. That is both an ideal of R and our bar, the integral closure. I'm going to put here another property that is going to be important later when you want to prove that the splinters are normal. A more conceptual way to cook it up is to consider this map and see is a so-called trace ideal. Okay, it just happens to be the image. So the point is like out of this, you construct a trace, right? That trace goes from here to here. Okay. So it's that. So it's literally the trace of this map. It's an ideal of R. That's a more conceptual way to think about it. Okay? So you remember that we invested in all the nonsense, and it's because you get things like that. And for example, this essentially is going to imply that splinters are normal. Okay? Which I let you do as an exercise. But here is the most important thing actually. Actually, it would be a consequence of this, but you can prove it directly. You can prove that C belongs, so it's a C ideal, i.e., it is compatible with all P's. Okay? This is, I let you prove it, it's not too hard to get it. And it turns out to be non-zero. I guess I let you prove that C is not zero, that there is something non-zero that lets you do that. Yeah. The reason is that if you look at lies at the pillar fractions of R, right? You get a field, and a field is normal. So essentially that implies that C Because C, the point is that C localizes where. Okay, and so this guy is not 0. What is the consequence of that? Whenever you see that, there's a punchline that you should think about it immediately. C is containing, oh sorry, C contains test ideal. Right? It is non-zero, and it is a C ideal. The test ideal is the smallest one, right? And so, corollary, if R is regular, meaning this is R, C is R, then R is normal. Let's take a minute to think about it, right? Like, what is the beauty out of it? That normality itself is governed. You know, the non-normal locus is cut out by an ideal, right? That just happens to be a C ideal. Therefore, normality, therefore irregularity is stronger than that notion of singularity, normality, right? There's a very nice proof. Okay, and also I gave you an example of what a compatible ideal would be. These sort of things. So compatible ideals govern normality phenomena like that. Okay. Any questions with that? So I'm gonna let you prove the following two. Exercise. If R is a pure, actually F injective too, you can try that. It is not normal actually. It's not true that the pure rings are normal, but they are weakly normal. Which essentially is related to the fact that this has to be radical, right? If R is a pure, then this guy being here means that it is radical. Okay, so if you think about what that means, you're going to get that it's weakly normal, which means the following. So notice that normality means that any monic integral equation, so if you have the solution of a monic integral equation, that solution has to be in R, right? And so, if you have x to the p in R for x in the field of fractions, right? This can be written down as xp minus R, right? Equals 0. So this means that x satisfies a monic equation. That is the extraction of a p root. If it is normal, then x has to be in R. So weakly normal just means this. Weakly normal means that when you extract p roots, they live inside here. Actually, I think this is the characteristic, but it's this too. Anyhow. Okay. Something that's a weakening over there.
You say that if R is a pure injective IT. So you said that if R is a pure or an injective, and
yeah,
you say right next to the injective IT.
It is. Oh. It is a weakly normal. Yeah. So if purity is not good enough, you know, to have normality. Okay. Let me hit you with an open problem that I really like. Now that we know that R is normal, it makes sense to ask the following. Open problem. Take R. A regular domain. In particular, normal. When you have such a ring, what can you define automatically? That we learn here, the divisor class group. Right, out of that, you get the divisor class group, sorry, which that we denoted by CLR. Right, this is a Z module, it's an abelian group. So the open problem is whether or not this group is finally generated. So this is finally generated. Okay, I can give you a few remarks about this. So, well, we may assume this, so the point is that we can work in the local case. That's fairly standard. And the point is that the divisor class group of R is inside the divisor class group of the completion. The completion just makes it larger. So you can assume that R is complete. Okay, and you can also assume that R is this guy is torsion free. The reason is like essentially we know, for example, that the torsions of group is finite. Right? If it were finally generated, the torsions of group has to be finite. Right? It is one of the structure theorem for finite generated modules or PIDs. And moreover, this is something I worked out in my thesis, is that this is going to give you some sort of finite extension where the divisor class group of R modulo the torsion is inside CLS and this is torsion free. Okay. I'm not giving the details here. So the point is like this is the progress so far. In dimension 2 is being worked out. Actually, we know exactly that the divisor class group of regular surfaces are finite. So even stronger for finally generated, right? But yeah, so here you have an open problem that you may want to if you feel like so. Okay? And it's a super cool one with a whole bunch of cool applications. And it's urgent, you know, it's like an important thing to know. There is a more general version of it. So the more general version is as follows. The point is also that since it is normal, it has a nice so-called Cox ring. So R, so again, a regular domain, it's going to have a Cox ring, which is this thing. So it's going to be a huge ring, but you can see why it's going to be a generalization of that because you sum over the divisor class group. Okay. And here, we're going to take all these things. Okay, and so, well, this is the structure as an R module, right? But when you put D equals 0, you're going to get R. And this is what, well, these are all R modules, right? So this is an R module. But I need to tell you what is the algebra structure. But the algebra structure is given by what you expect. Right? If I have two elements here, and I multiply them together, I get an element there. Right? So, you got that. And what do you think is a conjecture? This thing is the theorem. If this is not finally generated, there is no hope. Okay, so this thing here is an theorem, or even stronger, you can ask, finally generated R algebra. If it is a finally generated R algebra by Hilbert's basis theorem, whatever, right? It's going to be an theorem. But then you can try to prove it is an theorem. Okay. So this is part of a much bigger conjecture that says that globally regular varieties are modally dream spaces. And the first thing to do is to look at the singularities it has and guarantee that this happens. Okay? So this is sort of telling you that this is conjecture that these singularities are good for the operations of the minimum order program, in a sense, but we gotta get this one first. Okay? So if you're looking in problems to work on, this one is a good one. And essentially this is 0 progress. Okay? The best result perhaps is something like something along the lines if the full Cauchy algebra is sort of finite generated, and this one is something like that. But okay, let's see. Oh, there are particular cases of this too. So another thing that is open is that you can take, for example, something like this. And you can sum over Z, or you can sum over N, it doesn't really matter too much. This thing is finally generated. Or Matherian. You can ask for which class of divisors on R this is true. For example, this is a more refined question that is very important. If R comma P, I'm going to take a pressure is purely regular. I think this is a more sensitive question. In other words, R is yeah, we define this, right? R is a regular along P, but it's also known as purely regular. Okay, yeah. So I think in the note we said that R is a regular along P. This is a prime divisor. This is a much stronger hypothesis than R being a regular. Okay. It implies that it is a regular, but it's much stronger. I think Pedro's going to tell us about that, so you can ask if then somehow this ring here is an theorem. Okay. So these sort of things are very open and very important. So I want you to see that there are many questions, okay? And the field is very open and interesting. Yeah, so these are just natural questions that come up out of having normality, different contexts in the rational geometry. But let's talk about different things. So now we know that regular rings are normal. And I want to prove a stronger property now. That's the fact that they are splinters. So let me come back to this thing I was saying here. That the conductor ideal is a sort of trace ideal. So let me make that precise. Well, any questions so far? Definition. Trace. Ideals. This is the following. You're going to take a finite extension. Remember that the finite part simply means that S is finally generated as an R module. Okay? And so out of this, we can cook up this map in a spectrum. That we understand very well as a finite code, right? The picture is that you have the spectrum of R, and so you have some velocity down. Okay? And so then we have the trace map. Okay, remember that this omega f was the upper strip of R. Right, and out of that you get a trace. It's something we have used several times. And the point is that we can look at the image of this thing. So remember that, well, if you want to be very concrete, this is just home R S R. And what are you doing here? You're taking all these maps and you are evaluating them at one. Okay, that's what this map is. So you can look at the image of that. That's a trace ideal of the finite extension. So every finite extension is going to give you a trace ideal. So, yeah, then I'm going to denote it by tau of f. And it's a bit confusing with the test ideal, but that's on purpose because there's sort of conjecture to be the same thing. So this is by definition the image of the trace. So we'll just write down like this. You can be very explicit and you can just say that these are the p's of one such that phi is in Q. That's an ideal. Okay. So this is the trace ideal of that. Or let's say, I mean, you can also say over S over R, you know? You can also write here. It's just notation, okay? So it's the definition here of this trace ideal. The idea is to think of it as a sort of compatible thing, especially when you start varying S. Okay, so let's see. Remark. Remember that all remarks means exercise for you. The point is that the extension splits. You guys remember what it means to split? It means that there will be a map going backwards that is R-linear, right? R-linear, such that when you do that, you get the identity. So there is an R-linear map going from S to R, sending 1 to 1. Okay, so this is splits. If and only if tau of F equals R. Right? That's sort of easy to see. Because if this is R, it means that phi of 1 is 1 for some phi. Right? So I guess I have written down with phi. But more importantly, I'm going to let you prove that whatever this cut out is a set of points P such that the extension is not split. Isn't split. You guys buy that? Is it reasonable? Here is a key observation. This guy where do you think it belongs? Exercise. It's not easy, but it's a very short proof, though. You have to really chew it well. But it's simple. So prove that. And actually it's not 0. Why is not 0? Because if I look at the generic point, I localize, I have an extension of fields. An extension of fields always is split because fields are wonderful. So this thing cannot be 0. To prove that, look at generically. What is the consequence? This ideal dominates it. Corollary. If R is a regular, then R2S splits. For all S. So this is the so-called splinter singularity. Definition. R is a splinter I don't know if you know this word, but splinter I don't know if it's a plant, but the splinter in Spanish, for example, would be astilla. You know, splints. It's a splinter if everything splits. If you have a finite extension, splits. Okay. So regular rings are splinters. Have you heard of the splinters before? This is the first time. Well, it's a very good first time. So yeah. So i.e. a regular implies a splinter.
So the corollary extension is finite, or is it any extension?
In the corollary, any finite extension. Yeah, I was thinking that we had the same one. So this one is finite. Yeah. So a regular implies a splinter. And for example, you can easily see that the splinter implies, well, a splinter, a finite implies like a split. Or a pure, right? In the finite case. Because if R is a finite splinter, well, it has to split the probeans in particular. So it has to be a pure. And open problem, show the converse. Show that a splinter is a regular. Let me do that as an exercise. So this is the most important open problem in the field. This is the most important problem in computer algebra, like that. Open problem. Splinters, what they find ones, are irregular. Okay? Prove that for your thesis and you get a job wherever you want. Okay? I'm gonna come back to it, but let me say just in word right now, this is not for Gordian rings and deviations from Gordian, like Q Gordian, this is not Gordian rings. And dimension less than 4. So anything else? It's over. But okay, so let me make a few more remarks about how this works. Where are we? Just as an exercise, basically using the same proof that the regular rings are normal, you can prove that the splinters are also normal. Okay, so the idea is like, well, the point is that they're supposed to coincide with the regular rings. Okay, so, but that has been very hard. It has been very hard. People have tried very hard to prove it or disprove it. At some point, there are some people saying that maybe it's false. Well, we don't know. Okay, but something people have tried, especially in Kevin and Kevin Tucker. They've been studying systematically what are the properties of splitter singularities. Okay, this okay. Let's forget about everything and let's just look at that as a very own thing. So you have that written down a whole bunch of papers that are very interesting. And the perspective here is to focus on essentially trace ideals instead of sort of compatible ideals. You see, they are a smaller class here, right? Like you can look at inside here. Let me write it down over there. I'm so hungry already. So let's look at this. Let's look at this. So you can look at this tau F inside here. And so they look at this sort of thing systematically. For example, trying to say that actually the conjecture is that these two things are equal. Conjecture. That would be stronger than proving that splinters are irregular. But the conjecture, open problem, equality here. There is an issue here. That is kind of subtle, but I'm going to fix it in a second. This is not a set. Right? I cannot just take tau f, parameterize it by all f. That doesn't give you a set. I don't know if you see why. It's like a set theoretic annoying thing, but it has an easy fix. Okay, so I'm going to take f. So essentially, what I'm going to do is that I'm going to take a set of this thing. So what you have to do is to fix a so-called absolute integral closure of R. This R plus. Okay, that's a big deal in the field. Maybe if we have a second course, we can go into that. But there is this absolute integral closure, and I'm going to take the S to be inside here. So I'm going to fix that, and I'm going to take the S's inside there, and that will give me a set. Okay, so and it suffices to look at that. That's the point. So this is finite. So what this is, R plus, by definition, what you do is that you take the integral closure of R inside, let me just write down like this, a fixed algebraic closure of K. In fact, it's supposed to take the separable closure, I think. Yeah. But that's what you do. And then inside there, you look at finite extensions. Okay? In fact, you can be finer. You can actually consider a smaller subset. The point is that they give the same set. You can look at things like that when so let me put it like this. I'm going to take the integral closure of L, and what you do is that you run over all possible, K is inside this huge thing, and here I can take just finite extensions. And I can take the integral closure of R inside that L. And I just run over all those finite extensions. Okay? Let me repeat myself. Fix an algebraic closure of K. That's important for set theory reasons. And inside there, take all the finite extensions of K. And then take the integral closure of R inside there. That's going to give you this thing. That's your S. And look at those things. These two things are the same set, actually. That's my point. Okay. And that lives inside there. That's easy peasy. Almost easy to prove. Okay, that's what gives you that irregularity implies splinters. There are more things here than there are here. So if this is empty, well, not empty, but if this is contracts to two ideals, that has to contract to two ideals. Okay, and so the open problem is to prove that they give you the same thing. The point is to prove that a compatible ideal is a trace ideal. Okay, so but they took this path and they sort of were studying the singularities this sort of thing gives you. So a splinter has a very own thing. So what would make sense according to what we did the other day? To look at the trace topology this gives you, the trace Zariski topology, right? Actually, you can verify that these things are going to have the same properties of trace of compatible ideas and logical coupled topology. Meaning essentially that they're formal lattice. This is a sublattice. Intersections is there, sums are there, and so on. So in principle, this gives you another topology. So you can take the spectrum of R and replace that by this trace spectrum, where you use this thing instead. And you can try to repeat an F-singularity theory out of that, based on trace ideals. And if you do that, actually, so I can go ahead and take these portions. But I don't know what is an explicit description of that. I don't think they did that, for example. But when you do that, the point is that the splinters become the irregular objects, the simple objects, you know? But of course, the conjecture that you're supposed to get the exact same theory. I mean, these two things are the same, conjecturally. Okay? As I was saying, for Gorenstein rings, this is the case. For Q-Gorenstein rings, this is the case. This was proved recently, actually. I was a postdoc in Lausanne. Actually, I presented in the print seminar the paper that proved this, a paper by Harshid and Thomas Polstra. I really would like to prove that, but it's based on something called the equational lemma, which is a very important technical thing to learn about. But I don't know where I want to have the time to get into that. But yeah, so this is the thing. So what I was saying earlier is like this gives you like for example, another example in which you may want to do that and see what happens. Actually, I think it would be super cool to see what the trace core map is. What is that explicitly? I don't know. But conjecturally, it should be the splitting prime. The Cartier core should be the same. Okay. But what I can say is that some people just say, okay, let's try to recreate sort of similar things for splinters to see what it breaks. Okay, and so, or the other thing is to try to prove that the splinters have the exact same properties as regular rings. So if you want to learn more about this, just look at the papers. I think there are like 2 or 3 papers about that by Rankeya Dava and Kevin Tucker. The splinters. Or splinter singularities, let's say. Okay, where are we? Oh yeah, well, one more open problem. It's related to that. Maybe a final remark. So what did we solve? We saw that the test ideal of R, right, is going to be inside the test ideal. The test, the trace ideal. When we run over, sorry. You see, I need this to be a set. So you cannot take an intersection over something which is not a set. It feels like that, but technically speaking, you can't if you work on some metal prime. Right, so this is why I fix that. And so here I'm going to take finite. We saw that, right? In that paper, in this set of work by Rankeya and Kevin Tucker, so they call this to be the trace test ideal or something like that. I forgot. But let's call it T plus. Okay. What do you think is a conjecture? But these 2 things are equal. Okay. Where are we? I'm missing a remark I wanted to make. Where is it? Here. Yeah, maybe that's definitely a final remark. That's another thing I wanted to prove, but I don't think we're going to have the time to do so. But this is another observation remark. This is a result of myself and Axel Speller. The point is that R is a regular if and only if you could say it's an omega F splinter, but what this means in practice is that whenever you have a finite extension, finite splits by an element of tau omega F. Let me just put it like that. So the point is that this lives inside omega F, right? Yeah, so the point is that this omega F will have a natural Cartier structure, so it's going to have a test module, and yeah, sure, a regular means that it splits, but it means more than that. It means that it has to split by a test element of this Cartier module. And conversely, okay? So you see the gap between a regularity and splinters. A splinter just like this, it splits, but it doesn't tell you anything else. A regularity tells you that it is split by a test element. So the point is to fill up the gap. Okay? So, well, if you want to try to prove all these things, maybe we can talk about it later. It's not like I have any ideas, but if you have ideas, we can talk about it. Okay? Try it. In your free time. How much time do we have? Yeah. Just another question you can ask is like, another question I really care about is like, well, for my thesis, I proved that the fundamental groups of irregular singularities are finite. Okay? It is an old problem to prove that the fundamental group of splinters are finite. Okay? And that's crazy. So, because we have no idea how to do it. What is the big gap? So the point is for irregular rings, you can rely on the signature. We haven't studied yet, but maybe you have heard of. Okay? But there is no signature type thing characterizing splinters. Okay? But where is the signature coming from? The Cartier course. You just measure the length of this R modulo I is. So perhaps if you can construct a trace core, and you look at it and you may try to see how formally you can cook up a notion of a signature out of this, things like that. So yeah, so let me just leave that over there. There are many open problems. Definitely you can try here. In which we need new ideas. Yeah, gonna stop there. Okay, final property. I think we have time today for that, and let's stop there. Theorem. Irregular rings are conformal. That's the second type of basic property they have and why we love them. How does it work? It's the following. Sure. Let me make a general observation here. This is a historic note that I think is good to know about. The notion of irregularity was born out of trying to prove certain things were kind of called particular certain rings of invariants. So what they did essentially was to prove secretly, Hoxha, Roberts, and maybe others, that they were F-regular. But they didn't call it F-regular, they just proved that they had that property. Therefore, that property will guarantee cosmopolitness. Then they oh, this is interesting, actually it's regular. That's actually the whole study of this. Okay, so just because they're cosmopolitan, they're very good to prove that things are cosmopolitan. So the proof is as follows. So let me start with a very general observation. So take C in R. Well, if R is a domain, I want Z to be non-zero, but I'm just going to say avoiding all minimal primes. Okay. Let me just say that C is in R series. You will see this notation very often. So I'm assuming that R is a regular, okay? So I know that by the definition of a regularity, if I consider this diagram, and here I'm going to multiply by C, internally, let's say, the Frobenius, right? What I know is that this is going to split if I take E sufficiently large, right? I'm guaranteed the existence of a map going like this, such that when I look at the whole diagram, I get the identity, right? But then I can apply the local cohomology functor to that. Well, remember that cohomology means that the local cohomology vanishes. Okay, so I'm going to apply the local cohomology functor to that to see what I have. So if I do that, what happens? So I get this here, I get this thing here, and you guys will remember that local cohomology, you remember that local cohomology doesn't see finite extension, right? So it completely ignores Frobenius. So what you can say is that, we have said this before, so I'm just going to ignore the Frobenius. I can put it here, technically speaking, but the tradition is not to, and sort of just look at the Frobenius action on that. So as a map of abelian group is the same thing. So all I'm doing is to ignore the homogeneous structure. So if I put the Frobenius proof forward, it's because I want to say it's an R linear map. But otherwise it won't be. It would be a Q linear map that we have talked about before, right? So I'm just doing this because first of all it's a tradition and it's clear. So what we're gonna have is this, and here we're gonna have multiplication by C. Okay. So if you want, you can also look at the notes where I just wrote the same argument with the Frobenius push forwards everywhere. So here, what I'm going to have is the cohomology of phi. Right? So complete this thing. And local cohomology is a functor, right? That's the point. So here I get the identity. So okay. So i.e. C. I'm going to take this operator, I'm going to multiply by C, is a split. Or is sufficiently large. In particular, injective. Right? A regularity implies that. A regularity implies that whenever it has a C that avoids the minimal primes, this operator acting on local cohomology is going to be injective. Even more, it's a split. Okay? Good. So what do we get out of that? so I claim that we're done. Because, so when you look at that, this actually has a property of implying that these guys are going to be 0 for all I less than the dimension. Why? Because I claim that there exists a C, there is a C that kills all these guys. There is a C in the annihilator of all these things. Okay. And well, also, well, and also in our set. Okay. I claim that there is a C. I did that for any C that was just in here, right? But I claim that there will be one that kills all the local homology modules. And what does that mean? That if I take that C, that map is 0. Right? And so what do I mean? That the 0 map is injective. And the 0 map is injective if and only if the thing is 0. Right? So it will boil down to prove this property. Which is very simple actually. I can think of 2 arguments at least to do that. And we're done. Then we'll go for lunch. I guess you can go for lunch at 2 p.m., but I'm gonna go now. So let's see. Actually, it's something I forgot to ask you to prove. So you have 2 paths. So let's prove that there is such a thing, right? That's my claim. So there exists, well, let me say that if I look at the annihilator of all these guys, let me call D the dimension of R, intersected with the elements of weighted all minimal primes, also known as non-zero divisors, okay, or regular elements almost. I claim that this is non-empty. Why? Well, because actually, this is the exercise I forgot to ask you to do at some point. This ideal here cuts out the non-Cohen-Macaulay locus. I forgot to ask you at some point to prove that. Maybe I did, I don't remember. I think we did. So I asked you to prove that the Cohen-Macaulay locus is open on a material ring. And actually, its complement, it's cut out by that idea, which makes sense, right? Because it makes sense. And this cannot be 0. Or it cannot be completely contained here. Because generically, R is a field. And fields are Cohen-Macaulay. That would be it. But if you don't want to do this exercise, there is a simpler reason to see why, which is the same thing, honestly. So let me argue that real quick. Because that's considered to be the hard part of this proof. To cook up that C. So how do you do that? So the point is that I may assume in this whole business that R is complete. It's local complete. Because this is definitely something we proved. To prove that something is Cohen-Macaulay, we can assume that it's complete. Okay. And so what I want to say is that then I can say that R, this is R, right, is a quotient of a complete regular local ring, right? And this is prime because I'm assuming that R is the domain actually for root, or not, or yes. What am I doing? Well, yeah, because what I'm doing is that the regular implies because I'm fully know that the regular is product of the domain, so I may assume that R is the domain, so I may assume it's the primary field here. Blah blah blah. Right? And so what happens is that if I do this, right, and this essentially is gonna be, you know, a ring like this. The point is that by duality, this duality, I know that this guy is the dual of this X module. I have to take the dimension of S. So I'm going to say N is the dimension of S minus I of R S R. Okay? Even as S modules, therefore as R modules. That's just duality, right? But that has the advantage. So by duality, then if I want to kill this, all I have to do is to kill that. Because duality is faithful, it's a duality, it's an equivalence of characters. So, and that's much easier to kill. Well, the point is like, I know better how to localize the thing. And so, what I can do is I just can go ahead and try to see. So essentially what I want to do is to look at this, localize a P, and prove that it's not zero. Then there is a type here. No, I want to prove that it is zero, sorry, yeah. Yeah, sorry. So I'm going to look at this. N minus I. And I know I can commute this. SP. And what is R localized at SP? Is the field of fractions of R. Right? K is actually SP, P, SP. The field of fractions of R is the residue field of S and P. Sorry, it's just like I'm in a rush because I'm very out of time. So you get that, right? And what is so? I want to adjust this. So I want you to notice. Well, let me do it here. What is this thing now? So here you have to do the math carefully. Let me do it very, very carefully. I claim that this number here can be rewritten as dimension of SP minus I minus D, where D is the dimension of R. Why? Because the dimension of SP, which is the height of P, plus the dimension of R, by one of these things about coloring, which is this guy here, that add up to the dimension of the whole space. This is the, yeah, I'll send the book note from you, the book review, okay? And so there you are, right? Because then in principle, you can apply duality again and see that, or just say that this ring here is a field, but it is called Macaulay, right? And so this thing is going to be zero if this is less than zero. Which is the dimension of K. So it's going to be zero if I is less than D. And so it is zero when you look at a P. So it is killed by something not in P. That's the okay. So yeah, let me stop here. Sorry for going over time. But for sure, most definitely, if there were a qualifying exam here, then in other places, this would be a standard question. Prove that regular rings are conical. And you have to argue the existence of that. Okay. Okay, let me stop.